All right, today we're going to pull back the curtain on the elegant mathematical secret that actually governs every single orbit in the cosmos, from planets all the way to comets. Turns out, it's just one equation that explains it all. Let's dive in. Have you ever looked up and just wondered why the Earth follows this nice, predictable, almost circular path, but then a comet can just swing by one time and then vanish forever into deep space? How can the same laws of physics create such totally different journeys? Well, that's the big question we're going to tackle. Well, it turns out these paths aren't random in the slightest. The stable ellipse of a planet, the escape path of a space probe, and that wild flyby of a comet, they're all, believe it or not, part of the exact same geometric family, the conic sections. And here is the best part. To understand this whole family, you don't need a bunch of different rules for each shape. Nope. Instead, we can use one single, super powerful definition that's built on just 3 key ingredients. And this is what unifies everything. Okay, so ingredient number 1, the focus. This is super simple. Just think of it as the gravitational anchor point. The big boss. In our solar system, that's the sun, of course. Everything is being pulled toward that one single point. All right, the second ingredient is a little weirder. It's called the directrix. Now, this isn't a real thing you can go out and touch. It's more like a ghost line, a reference line that we draw out in space. But trust me, it's absolutely crucial for defining the geometry of the orbit. So, how do these two things, the anchor point and this ghost line, actually work together? Well, it all comes down to a really cool, simple rule. For any point along an object's path, the ratio of its distance to the focus versus its distance to the directrix is always the same. It's a constant. And that constant ratio, it has a name. It's called eccentricity, and we just call it E. This single number is our third and honestly our most important ingredient. It's like the magic dial for the universe that determines whether an object is going to be locked in orbit forever or if it's just passing through. So you take these 3 ideas, the focus, the directrix, and this magic number E, and they all come together in one incredibly powerful formula, a single equation to describe every single possible path through the cosmos. And there it is. Now, I know, it might look a little intimidating at first, but the key, the real hero of the story, is that little variable E for eccentricity we just talked about. That's the number that controls absolutely everything. Let's just break this down real quick. As we know, E is the shapeshifter. That P there, that's just the distance from the focus to that ghost line, the directrix. The sine or cosine just tells you if the orbit is oriented more up and down or side to side. And the plus or minus sign, that just tells you which side of the focus it's on. See, they're all just simple parameters. The real story is all in that E. All right, enough theory. Let's actually put this to work. We're going to look at a few equations now and use eccentricity to decode the exact shape of the orbit they represent. Okay, this right here, this is basically the Rosetta Stone, the cheat sheet for cosmic orbits. If E is less than 1, you get a closed, stable ellipse, kind of like Earth's orbit. If E is exactly 1, you get a parabola. That's the path of an object takes to just barely escape gravity. And if E is greater than 1, you get a hyperbola. Whoosh! That's the path of a comet, just slingshotting through the solar system, never to return. Okay, first example. Our whole goal here is to find E. Now remember, the standard form of our universal equation needs a 1 in the denominator. This one has a 3. So to fix that, we just have to divide the top and the bottom of the fraction by 3. And when we do that, the number multiplying that sine function becomes 2/3. And that is our eccentricity. And since 2/3 is, of course, less than 1, we know this equation has to describe an ellipse. This could be the orbit of a planet, maybe an asteroid, something that's forever bound to its star. Let's try another one. Same exact process. To get that 1 in the denominator where it belongs, we're going to divide both the numerator and the denominator by 2. So after we simplify, we see the number in front of the sine function is just, well, it's 1. So our eccentricity, E, is exactly equal to 1. And this is a perfect example of an escape trajectory. This is the path of something that has just hit escape velocity. It is breaking free from the gravitational pull of its focus and just heading out into the cosmos. Okay, last one. Here, to get our standard form, we've got to divide everything by 4. And when we do, our eccentricity E is revealed to be 5/4, and that value is clearly greater than 1. So you know what that is? That's a hyperbolic path.
You can just imagine an interstellar object visiting our solar system for the first time. It gets pulled in by the sun's gravity, slingshots around it, and then gets flung back out into deep space with even more energy than before. It's a one-time visitor. So let's just bring this all back home. We started with the cosmic puzzle, right? This whole zoo of different orbital shapes that looked like they all followed different rules. But what we've seen is just this beautiful simplicity hiding underneath it all. It's not chaos. It's one system, governed by one single equation, where one little number, eccentricity, defines the destiny of any object orbiting a star. I mean, the fact that all that cosmic diversity can be described by such a simple mathematical principle is just astonishing. It really makes you wonder, what other profound universal patterns are out there, just hiding in plain sight, waiting to be decoded?